I uploaded two Python notebooks, one with an incomplete code and another one with the complete code. Whether or not you want to follow the incomplete code, maybe fill in the some of the code that I'll be writing, or you want to look at the complete code, that's up to you. Yeah, whatever you think it's easiest or most convenient. First of all, importing all the necessary modules. Then I also I had actually already uploaded this mesh at some point. I don't know when, but I uploaded this mesh. So this is part of the incomplete code as well. Oh yeah, this is the incomplete code. Um, yeah, just reading the mesh, no need to do anything, and we'll basically store all the nodal information in this elements array, and then all the nodal coordinates in this node x array as usual. There's a variable for the number of elements, there's a variable for a number of nodes. So the mesh is basically as usual. So in this case, there's 576 nodes and 512 quadrilateral elements. Then the other thing that I have in the incomplete code is something that you can just look up in the book, which are just the shape functions and derivatives of the shape functions. Note that for the quadrilateral elements, it's easier to have the shape functions in terms of the parent domain coordinates xi and eta. So we don't really have, and we've never done this in class, we've never found the shape functions in terms of x and y, always with respect to xi and eta. And so you can just look up, what are the different shape functions, there's 4 of them, and then basically just take derivatives with respect to xi and eta. So that's it. So no need to code that on your own. Basically, this is something you can just look up and then just write as you find it. Just execute that. Then plotting of the mesh, and again, this is not code that I want you to really figure out on your own. So I gave you this this little piece of code to plot things so you can create a figure. And then you need, in order to plot the quadrilaterals, you need to get the node numbers for a given quadrilateral. So I have a loop over elements. For each element, I can find the nodal points, and I can create polygons with the nodal coordinates of the 4 points. So you can see here that I have, these are the xy coordinates of the node 1, xy coordinates of node 2, xy coordinates of node 3, and xy coordinates of node 4, and it will create the quadrilateral. And then you can assign a color. In this case, I'm assigning, for the color of the quadrilateral, I'm assigning the x coordinate of the node 1 of the quadrilateral. And that's just arbitrary. That's just to have some color. Yeah, so nothing, just nothing related to the class, really, just a way of plotting quadrilateral meshes. Now here is where there's some gaps in the code. We have to assemble the stiffness matrix and the force vector. The first thing to remember would be, what is the size of the stiffness matrix? And this is different from what we have done for the heat transfer problem, because in the heat transfer problem, the unknown is the temperature, and that's a scalar, so we only have one unknown per node. But here it's a displacement field. Now each node has two unknowns, displacement in x, displacement in y. So actually this is 2 times number of node, 2 times number of node. And then for the force vector, that's going to be 2 times the number of node. Then we have our usual loop over the elements. Then, as usual, we want the nodes that make up this element. This is a quadrilateral, so we have 4 nodes. And these are always stored, for element I, elements I, 0 has the first node, elements I, 1 has the second node, I, 2, I, 3. I don't think I have it later on. Oh, I did it afterwards. But it would help. I did this in lecture 24 code, but it helps to put these guys into a single array, and you'll see why later. And if you haven't looked at the video of lecture 24C, then go to that one, because I explained that as well. So it will help to put it in in an array. Then once I have the nodes, I can go and get the coordinates of each node. So again, I need to access the node x vector, and then node x, node 1, 0, that will be the x coordinate of the first node of the element. Node x, node 1, 1 will be the y coordinate of the first node of the element, and so on. I have 4 elements, so I have these 4 pairs of x and y. And then we need to do the integration. So at this point I have the nodal coordinates, and then I would need to do this integral right here. I need to do this integral, which means I need to, for example, if I use Gauss quadrature, I need to loop over the Gauss quadrature points. Now, that's actually something that you are going to do in homework 6, and then I'm going to give you the simple version, which is a single point integration or reduced integration. So I won't need a loop over the integration points. Otherwise, you would need a loop. You would need, for IP in range length of Gauss points 2, or whatever integration number of points that you have for the integration. So you would have to have a loop over the integration points. But in my case, I'm gonna do a reduced integration, which means I only need to evaluate at a single point, and that is just psi and eta equals 0, 0. That's it. That one has weight, so this would be single integration point. That one has weight 4. This is something you can look up. And then now for this psi and eta, I need to evaluate x and y. And that just means stating the isoparametric map. So this would be n1 of psi and eta, right? Let me just make sure that I named it just n1. Yep, so just n1 evaluated at psi and eta, which in this case is 0, 0, times x1 plus n2 of psi and eta times x2 plus n3 of psi and eta times x3 plus n4 of psi and eta times x4. And the same for y. So n1 times y1, n2 times y2, n3 times y3, and 4 times y4. So that's the x and y corresponding to psi and eta equals 0, 0. Then I need the Jacobian matrix. So the Jacobian matrix is these derivatives of the isoparametric map. So derivatives of x and y with respect to psi and eta. And then that just means basically taking the derivative of the isoparametric map. So what would that be? So that would be dn1. The only thing that depends on psi and eta are the shape functions. So I need dn1 dxi of psi and eta times x1 plus the derivative of the second shape function times x2 plus derivative of the third shape function times x3 plus derivative of the fourth shape functions times x4. And then that's derivative with respect to psi, and then same but eta. So dn2 the eta, dn3 the eta, dn4 the eta. Let me just make sure that I named them like that. Yeah, so dn1 dxi, dn1 d eta, yes, I named them like that. For y, it's going to be the same. So this is going to be derivative with respect to psi times y1, derivative with respect to psi times y2, and then the last one is going to be derivatives with respect to eta times y1 times y2 times y3 times y4. So again, isoparametric map. So basically the map from psi and eta to x and y, that's just sum of shape functions times nodal values. The Jacobian is the derivative of the isoparametric map with respect to psi and eta, and that's again sum of derivatives of shape functions times nodal values. With that, I can assemble my J. So my J is just this matrix, dx, dxi, dy, dxi, dx, d-eta, dy, d-eta, just as I have here. And then I will need the inverse later on, so I can write down the inverse. Well, I can calculate the inverse. I also need the Jacobian for the integration, so I just calculate the Jacobian. And now what I need is, I need to get the B matrix. At the end of the day, what I want is this B matrix. And this B matrix needs derivatives of the shape functions with respect to x and y. Right now, I only have derivatives with respect to psi and eta. So I can get the derivatives of the shape functions with respect to psi and eta, but I want the derivatives with respect to x, y. So what I need to do is just multiply by the inverse of the Jacobian. So this is why I have this right here. If I have the derivatives with respect to psi and eta, I can multiply by the inverse of the Jacobian. I will get derivatives with respect to x, y. So I just put the derivatives with respect to psi and eta in a vector. So that just means, for example, derivative of n1 with respect to psi and eta, I have it. It's just evaluating the function, but I need to put it in a vector so that it makes sense. Here now, I want the derivative of n1 with respect to x and y as a vector. So that's just going to be np dot inverse of the Jacobian times the derivative with respect to psi and eta. So hopefully you see that this line right here is exactly this for the first shape function. I put in a vector the derivative of n1 with respect to psi and eta. When I multiply by the inverse of the Jacobian, I'll get the derivative with respect to xy. Then for the second one, this is just exactly the same. So now I just have, for second shape function, I have derivative with respect to psi and eta. I multiply by the inverse of the Jacobian. That gives me derivatives with respect to xy. And then for the third shape function, exactly the same. For the fourth shape function, exactly the same. So now I have all the derivatives with respect to x and y. Now I can assemble my B matrix. So the B matrix is always this 3 by 2 times the number of nodes per element. So in this case, 3 by 8. And you can see that I just need to write, so for the first row is going to be derivatives with respect to x intercalated with zeros. So I can write that. So this is going to be an array, right? And it's going to have 3 rows. For the first row, I need grad n1 xy 0. So that will be the derivative of n1 with respect to x times 0 times grad n2 with respect to xy, the x component, times 0, times grad n3 with respect to xy, x component of that, 0, and then grad n4 xy, the x component of that, 0. So that's the first row. Again, derivatives of n1 with respect to xy component 0, that just means partial of n1 with respect to x, 0, partial of n2 with respect to x, so the 0 component of the gradient of the shape function. Then for the third shape function with respect to xy, again, that's a vector and it has x and y, so I just take the 0 component, 0, and then again, gradient of n4 with respect to xy is a vector with x and y components, I just take the x component. And then for y, I just have 0, comma, and let me just copy this and then change 0, comma, and now I want the y component, 0, comma, the y component, 0, comma, the y component, 0, the y component. And then the last row is going to be the switch derivatives. So now I have the y component followed by the x component, and then the y component followed by the x component for n2. So the y component followed by the x component, and then for 3 I also have the y component followed by the x component, and then for 4 I have the y component followed by the x component. And I have way too many, oh, because I should have started here. And what am I missing? So that's correct. I think I need to close this here, and then I need that one, which is close here. Yeah, perfect. All right, so I have the B matrix, again, 3 by 8. Then the D matrix, that's just the material properties. I actually forgot to put it on the problem statement, but let's say we have this material which is 200 gigapascal with some 0.3 Poisson ratio, and then you can just look up, again, this is in the book, and I didn't have it in this slide, but it's just a standard definition for plane stress. And now I need to do the integral. For the KE, if you actually were doing multiple integration points, you would have, plus equals. If you were in a loop inside of the Gauss quadrature, you have plus equals the weight, right, times the determinant of Jacobian times the function that you want to evaluate, which is just B transpose times D times B, right? Now in this case, because I'm using reduced integration, I don't have a loop over integration points. I just have K equals, so I don't have the plus equal, because I only have one integration point with weight equals 4, right? And then, so I just need, I don't really need to do a plus equal. I just have KE equals the weight of the integration point times the determinant of the Jacobian times, and then this actually should be NP dot, then the B matrix transpose, and then NP dot D BE matrix. So that's it. All right, so that takes care of the stiffness matrix, and I'm going to stop right here, and I'm going to continue the next part of the video with the force vector.